Hello, hello. Can you guys hear me?
Yes, we can.
Night before the midterm, have you guys tried to practice problems yet, or like how are you guys feeling so far right now? Much better than last time? Are we still a little bit scared for the midterm? Hello, hello. Let's see.
I think the worst part might be the NMR on history
Oh,
reference.
Recording in progress.
NMR, like I don't know how that's gonna be. Like, is it like the regular NMR problems that you guys had last quarters, where he gives you the IR, HNMR, and then you have to predict the product from that. Oh, predict the structure from that.
Maybe, honestly, I don't know, but the thing is, I've been doing so much practice for the reactions and stuff. I haven't looked at NMR that much.
Oh,
So
cute. Yeah.
yeah,
We could
that's
try going through practice NMR problems. If there's like someone to achieve homework or some practice problem,
oh
or
yeah, he does have some. Yeah.
yeah. So uh, let's see. You could share your screen on the achieve homework, and then I could like work through the NMR problem, and then share my thought process on how to do some of those problems.
Okay, yeah, sure. I can pull one up right now.
Okay.
Just give me a second to find it.
Yeah. I heard it's also no partial credit for synthesis somewhere.
No partial credit.
NMR. What?
Yeah, he says because if you can't do it in a lab, there's like no use in actually writing it down.
Oh my goodness.
Yeah, okay, this is one of them. I got the answer, but I have no clue how to actually do it. So
Okay. Do it.
this is the question.
Okay. So I'm gonna ignore this. I don't know what that is. I don't know how to read UV spectrum. I don't know EI mass spectrum. But I do know IR and HNMR. So for IR, the fingerprint region is 1500 and below, which is what we could ignore. So I'm gonna ignore that peak right there. But around 2100 to 2300 in the IR, if you see a sharp peak there, that's the triple bond region. So you're gonna either have an alkyne or a nitrile, right? And based on the chapter that we are on now, chapter 1920, we're talking about the carboxylic acid derivatives. So I'm gonna cross out the alkyne because it's most likely gonna be this nitrile, which is a cousin of those derivatives, right? So I'm gonna say that we have a nitrile somewhere in the compound. So that's the IR done. Let's look at the HNMR. So we have one hydrogen here, another hydrogen here, and 5 hydrogens here. Do you guys remember back in 118b when you guys learned about J values? If they have a matching J value of 17, what are these hydrogens to each other? Are they going to be cis, trans, geminal, allylic, or long range to each other?
Was it trans? I don't remember
Yep.
the values.
Yep, trans. Here are the values, and here's the relationship between the H's if they have matching J values. I think I remember the cis one is around 10, the trans one is around 16. Right. And there's something with 2 as well, but I forgot what that was. It was like allylic or geminal. Probably geminal. And then allylic or long range is like 6 or 7-ish. I forgot which one specifically, but here's the one I remember where I see that because these ones have a matching value of 17. I'm gonna say that we have a trans alkene, right? H, H. And that makes sense because this HNMR like peaks is between 4 to 6. Right? This one's a little bit higher than 6, meaning that this hydrogen here, like one of the hydrogens, could be bonded to something electron withdrawing, like some kind of carbonyl or alkene, right? Like 4 to 6 around that range is the alkene range for HNMR. Now, if we look at the 6 to 9 range, that's the benzene hydrogens, right? And because we have 5 of those benzene hydrogens, that shows me that I have a mono-substituted benzene ring. Like there's one group attached to the benzene ring, right? Because the other 5 are going to be attached to the other 5 open positions. Now, since I have my 3 components, the nitrile, the benzene, and the transalkene, I'm going to say that this hydrogen right here is going to be that 7.35 ppm peak on the HNMR, which is a little bit higher than the usual 4 to 6 alkene range. So that means that that hydrogen is going to be next to the benzene like this, right? Because it's attached to an electron withdrawing group, which is the benzene. And then I'm just going to connect the nitrile right here. Right, so that should be my final product. Oh, final molecule. Yeah. Nice. Okay. Yeah. Did that process make sense for the spectroscopy problem?
Yes, that made a lot of sense. Thank you.
Yeah, no problem. And then let me go over with you guys the IR and HNMR peaks that I think about, like on notability. So you can start sharing your screen, and then I'll show you what I think about for these problems. Right. And after that, I want to show you guys these charts for chapter 19 and 20. Right. Okay. So actually, I think I have a yeah. I already have an IR chart made ready. I think about just gonna be. So we saw that spectroscopy problem. We saw a peak at up to 2200, which is between the 2100 and 2300, which is the triple bond region. And this triple bond region is either an alkyne or nitrile, but I just went with the nitrile because we're in the chapter 1920 chapter, like we just talked about carboxylic acid derivatives. But then they didn't give you a molecular formula, so I didn't know how like you were distinguish between these two here from that problem. Right. So this is the IR here. Fingerprint region, you ignore that. 1600 is the C double bond C alkene. 1700 is the C double bond O. 2100 to 2300 is the triple bond region. Aldehyde 2700. And then the 3000 is the regular sp3 carbon hydrogen. So that's regular. If you see a sharp peak around 3100, that's going to be sp2 carbon hydrogen bond, meaning that it's going to be like a hydrogen bonded to an alkene carbon. Right. If you see a broad peak around 3300, that's going to be an alcohol. If you see a really broad peak that merges with the normal peak, that's a carboxylic acid. But if you have an alkyne, right, you have two kinds of alkynes. You could either have a terminal alkyne or you could have a internal alkyne. There is a way to tell the difference between these two for HNMR. If you have a terminal alkyne, you're going to have both the sharp peak at around 2100 to 2300 and the sharp peak at around 3300, right? This sharp peak at around 3300 shows the sp carbon hydrogen bond, which is this bond right here, and that confirms our terminal alkyne structure, right? The internal alkyne has no sp carbon hydrogen bond, so the internal alkyne would not have that sharp peak at 3300 at all, right? And then this is important for chapter 21, especially when you see a fang-like structure like this at around 3300, that's your primary amine. And I like to think of it like, since you see like two subpeaks that are broad here, I think of two hydrogens, right? Which are these two hydrogens attached to that primary amine right there. But if you just see one broad peak, then that's a secondary amine, where that one broad peak shows only one hydrogen, right? And I think it was a secondary amine as well, that secondary or primary amine, that it has something around this, around 1700 range from NH2 or NH, I think it was NH2, scissoring, right? That effect. And then the tertiary amine will have no peak here at all, because there's no hydrogens for the tertiary amine. Okay. For HNMR, this is what I think about. It's gonna range between 0 to 12, where 0 to 2 is the normal boring region, right? The regular carbon hydrogens, like that. 2 to 3 is gonna be my alpha region, where the hydrogens are gonna be alpha to either like 2 to 3, like alpha to an unsaturated bond. So let me give you different examples of that. Okay. It could be alpha to an alkene like this, right? This is the alpha carbon. It could be alpha to a carbonyl. It could be alpha to an alkyne, or it could be the terminal alkyne hydrogen itself. Like this is the terminal alkyne hydrogen right here. Right, so these are the different hydrogens that you see between 2 to 3. 3 to 4 is the electronegative region, where you see hydrogens attached to a carbon that's attached to some electronegative atom, right? X, where X could be oxygen, nitrogen, or one of the halogens, right? And the hydrogen is right there. Now 4 to 6 is going to be our alkene region, right? So let's say we have this alkene right here. We could have this hydrogen directly on the alkene, not the alpha carbon, but directly on the alkene itself. 6 to 8 or 9, 6 to 9 is going to be my benzene hydrogens. Right. And then around 10 is going to be my aldehyde hydrogen. And this aldehyde hydrogen here can have coupling. Right? You can see it as a doublet or a triplet. Can have what was it? Coupling. Subpeaks. You can see subpeaks. Right. And then around 12 is the carboxylic acid region. Right. So if they do give you CNMR as well, the biggest thing for CNMR is to tell the difference between aldehyde and ketone versus the carboxylic acid derivatives. So between 180 and 220, that's going to be ketone or aldehyde. Between like 160 to 180, I think, are the carboxylic acid derivatives. So your acyl halide, your anhydride, your ester, your carboxylic acid itself, your amide, right? These carboxylic acid derivatives. And I remember doing one spectroscopy problem where I just totally ignored the CNMR, but then I just used the IR and HNMR, and there were like two molecules. Like I had one that was very similar to the key, but the key was more correct because they had to use the CNMR to tell the difference between this and this. Right? So that could be helpful for some spectroscopy problems, but you get most of your information from the IR and HNMR anyway. But if you know how to read the other spectroscopy tools, then that's good too, just to confirm or get more information. Right. How do you know if it's the benzene? Oh, if the benzene is monosubstituted in the NMR? Yeah. So let's talk about benzene, which is going to show up between the 6 to 9 ppm range. If they show like a peak around 7 or like a 7.65, and they say 5 H's for the HNMR, these 5 H's here have identical chemical environments, right? So these are the 5 H's attached to the benzene ring. If we had another R group attached to it, like let's say another R group there, substituting the place of the hydrogen, then we would only have 4 benzene hydrogens. But because they gave that 5 hydrogen information, I know that this is monosubstituted. Yeah, that's okay. I understood the question. Hey. But let's see. How many benzene hydrogens would you guys expect if there's 2 substituents on the benzene? Uh-huh. Yeah, no problem. Yeah, 4 benzene hydrogens. And there's 3 patterns that you can see this in: ortho, meta, or para, right? And these are going to be for your di-substituted benzenes. Right? Where ortho is going to have your 2 substituents ortho to each other. Meta is when you have your 2 substituents meta to each other. Para is when you have your 2 substituents para to each other. Right? And I'm going to give you guys the different unique hydrogens in different colors. So ortho will have 4 different unique hydrogens. Meta will have 4 different unique hydrogens. But para will only have 2 unique hydrogens, 2 unique sets of hydrogens, 2 unique sets of hydrogens. Okay, and we said earlier that the benzene hydrogens are going to be between 6 to 9. So this is where you will find the peaks here. 6 to 9 for benzene. So if we look at the blue hydrogen for ortho, 1 neighbor, doublet. Pink has 2 neighbors, triplet. Purple has 2 neighbors, triplet. Green has 1 neighbor, doublet. For meta, blue has 1 neighbor, doublet. Pink has 2 neighbors, triplet. Purple has 2 neighbors, triplet. Oh, no, purple has 1 neighbor. Purple has 1 neighbor, so doublet. Green has 0 neighbors, so that's singlet. And this singlet here is a big indicator of meta, right? And for para, the blue hydrogen set has 1 neighbor, doublet. Pink hydrogen set has 1 neighbor, doublet, right? But each peak here represents 2 hydrogens, 2H, 2H. Whereas the other ones represent 1, 1, 1, 1, 1, 1, 1, 1 for each. Right? But they will all add up to 4 benzene hydrogens, 4 benzene hydrogens like that. Right? Yeah. Last question on the chapter 21 practice. Yeah, let's do the last question for chapter 21 practice. copy this. Oh, that I already see typo. There's a typo here. If the let's see, the real answer should be E. No reaction. But what did they put as the key for this? Because I think one of these is supposed to be an amine for reductive amination, right? Because when you see NABH3CN, this is a sign of reductive amination. They said the answer is D. Okay. Yeah, so if the answer is D, then our amine is going to be looking like this, right? Where we have a secondary amine. So to predict the product quickly for reductive amination, what you're going to do is substitute the carbonyl with the amine minus one hydrogen. So that's what they did, right? When we do reductive amination, we're substituting that carbonyl with this nitrogen right here minus the hydrogen. Before, this nitrogen had one hydrogen. Now this nitrogen has 0 hydrogens. And that's how you could predict the product quickly for reductive amination. Okay. But let's change it up and say that the amine was the other one, and the second reactant stayed as a carbonyl. We still do the same thing for reductive amination. If you get these like NABH3CN in acidic conditions, pH of 3 to 4, you could see HCl. We're still going to do the same technique to predict the product quickly. Substitute the carbonyl with the amine. So we're going to have the structure here. This amine, right, minus one hydrogen. Before, it's going to have one hydrogen, but now when we predict the product, it's going to have 0 hydrogens. Let me make this go down. Right. And it's part of a 6-membered ring, so it's going to be boom, like that. So this would be your answer for these two sets of reactants for reductive amination. Right. But since I said the answer was D, this part is supposed to be the secondary amine right here, no carbonyl. Right? Because reductive amination is saying you have a ketone or aldehyde plus one of these amines, ammonia, primary or secondary amine, reacting with acidic conditions in NABH3CN to get a more substituted alkene, amine, you could say, more substituted amine, right? Because we see in this example, before we had a secondary amine, but we created a tertiary amine right here, tertiary amine right here. Yeah. Could you also do 23 on chapter 20 practice? Yeah, 20 on chapter 20. Let's do it. This is to chapter 21. Oh, no. 20, number 23. Number 20. Ooh. This. Oh yeah, the notes for the sessions are uploaded on the school, so you guys can access that to review, and the recordings as well. This is why I'm like copying and pasting the problems to a separate document, so I could post these for you guys to review in one page after. A multi-step preparation of propyl, propanoate. There should be a space here between propyl and propanoate, right? Which looks like this. 1, 2, 3. 1, 2, 3. Oh, wait. Okay, so we're forming this as the product. Let me make sure that's right. CO2, C. What? 1, 2, 3. 1, 2. Oh, I see what they're doing. Yeah. This is the propyl part. This is the propanoid part. Okay. And that would require the use of how many of the reagents below? What reagents would you need to use if you only had one propanol to start with? Okay, so if you had this to start with, which I can already see that this highlighted portion here, which I'm going to highlight as the propanol, is going to be this part of the molecule here, where we could make a cut right here and see how we can combine this. I thought only Jones works, but it says to work. Okay. See. So Jones right here will not convert this into the ester, but would convert this into the carboxylic acid. This. Right. Which yeah, so Jones with one propanol would not give us this.
But would it be able to react again with the propanol? So you'd have the carboxylic acid with the propanol, and then would it make the propanoid?
Yes. If it reacts again with the propanol in acidic conditions, then this is special esterification that can form this product here. Yeah. So if we react with this up again in acidic conditions, then it could form that. Yeah, that would work. Right. So it said 2 of the above. The answer they said was A. Let's check this. 1 propanol NaCN. NaCN, no reaction, no good leaving group. 1 propanol acid, no, not good. 1 propanol. So no, there's no halogen here, so we can't make a Grignard reagent. No. Acid. Wait, what? Wait. Was the answer they said was A? They're scamming us. Oh my goodness. Scam. See, what if this was bromine? And then you do Mg to make this MgBr. And CO2, acid workup. Whoa. OH. And then if this reacts with propanol again, well, no, but then this is, yeah, that's not even a halogen. I think this question has a typo or something. Maybe you need acidic conditions like oxidize, and then H3O plus is the second thing we need. Oxidize. For this right here, we do oxidize it to the carboxylic acid, and then we would have to use propanol, 1 propanol, again in acidic conditions with H3O plus to get this here for sure esterification. This one here is trying to do SN2, but there's no good leaving group here. We can't do SN2. And even if it does go through, that's going to create a nitrile, not the ester. There's 1 propanol here. like that should be the same thing as this. That's just gonna protonate the alcohol to OH2 plus, right? To give this oxonium ion here, which is a good leaving group, but will not give us the ester. This one's trying to do Grignard reagent, but we don't have any halogen here, so there's no reaction there. So I don't know what's going on with this problem. I'm thinking that's all we need, which is yep, right. This one here needs first step of that. Second step, H3O plus. But usually when you see H2CrO4, it usually just comes with H2SO4 and water. It comes in acidic conditions. So the acidic conditions is usually provided with H2CrO4 as well.
Brian, can you explain why NaCN doesn't work with the primary alcohol again?
Yep. If we try to do NaCN with the primary alcohol, we do have a good leaving group, but this is a bad leaving group. We have a good nucleophile, but we do not have a good leaving group. This is a bad leaving group, right? So this is electrophilic, but we don't want to kick out that leaving group. It's a bad leaving group. But if we had something like a bromine attached to there, which is a better leaving group, good leaving group, we can do NaCN for SN2. So the CN minus can come in, attack this electrophile, kick out that leaving group to give us the nitrile here, and Br minus side product. So none are right. As it's drawn out right here, I would say none is right, because this looks like it's just doing Jones, which is gonna get to the carboxylic acid. But then the second step would need to be 1-propanol again in acidic conditions, just to make it more clear that we are going to get to that ester. So I would think the answer is E for this. Like it wants the Jones and then the thing about to get the product. Yeah. Right. So it would make more sense if we had H2CrO4, H2SO4 water. And then second step, it's like another version of itself in acidic conditions. The first step, oxidize the primary alcohol into the carboxylic acid. And then second step, Fischer esterification. Like that, to get the final product. Okay. Yeah, I think this problem is worded, let's see, a multi-step preparation of propylpropanoate from only 1-propanol would require the use of how many of the reagents below? What reagents would you need to use if you only had 1-propanol to start off with? Yeah. As it's drawn right now, E, but if this one had more like stuff to it, then this one could work with the Jones.
Brian, can you do 21 question 9?
Yeah, chapter 21, question 9. 21, question 9. This one. Okay. Yes. So for this one, you have to recognize the reagents and associate those set of reagents with a certain reaction. Right. So this is where when you do practice problems, it's good to label each reaction as you're predicting the product. Right. do you recognize these set of reagents? Have you seen this somewhere before? Br2 KOH H2O. You might see KOH in the form of NaOH. Yes. These set of reagents here is a big indicator for Hoffman rearrangement reaction. And then once you identified the reaction that this is doing, then you have to know like what the reaction does, right? The reaction is going to have a primary amide working under the reagents of Hoffman rearrangement to get the primary amine, right? And the biggest feature of this reaction is that we are removing the carbonyl, right? So this would subtract one carbon from the carbon skeleton. So what we're doing is we're having this whole amide right here and converting it to an amine like that. Where this should be the answer because we are also getting rid of this carbonyl, right? That this carbonyl goes away, goes bye-bye, right? So it's not going to be E, right? Because we still have that carbon right there, which was the carbonyl carbon. But what reagents, what set of reagents would give us answer E? Like if we wanted E.
Lithium, aluminum hydride?
Yes. Lithium aluminum hydride with acid workup would give us E. And that just completely cleaves off the carbonyl to get that primary amine, where we still maintained the same number of carbons. But if you see one less carbon, then that's going to be a big indicator for Hoffman rearrangement. And the reagents for those are Br2 base in water. Huh? Okay. So let me show you guys this chart for chapter 19 and 20 that will help you guys organize the reactions better. Let's talk about reduction of the carboxylic acid derivatives. Right. And do you guys know the reactivities of the derivatives, like the order that they are in? Like what's the most reactive derivative versus what's the least reactive derivative? Me, yeah. Okay, so halide, anhydride, ester, amide. Yes. And where would carboxylic acid fall under this list? Like what is it similar to? What is a carboxylic acid near before ester? So more near ester. So it has a similar reactivity with ester. Right, so you could think of us in between anhydride and ester. In between anhydride and ester. Yep. Nice. And then nitrile would be below amide. Right. So acyl halide, anhydride, carboxylic acid. So the way I'm drawing it is that I'm drawing the top molecule, the most reactive, and then going down is going to be decreasing reactivity. Right. But ester and carboxylic acid are going to be very similar. Carboxylic acid is a little bit more reactive, but the difference is not very big. Amide, and the cousin of these derivatives, nitrile. Right. So let me show you guys this. The four reducing agents that I'm going to show you in this chart are going to be okay. The strongest one, lithium aluminum hydride. Second step, acid workup. the weaker one, sodium borohydride, acid workup. Dibol, and then the really weird bulky one, lithium triturbotoxy aluminum hydride. Yeah, so these are the 4 reducing agents that you need to know for these derivatives, right? When you react these together, this is what you would get. And I wouldn't memorize like this chart without understanding it. It's best if you understand like what's going on, and then like everything in this will make more sense, right? Let's start with the strongest reducing agent, lithium aluminum hydride. This strongest reducing agent here is going to react with all of these derivatives, right? So when it reacts with an acyl halide, you're going to get primary alcohol, anhydride, primary alcohol, carboxylic acid, primary alcohol, ester, primary alcohol. Right. So everything would be reduced into a primary alcohol except the ones with nitrogen, right? Like the amide and nitrile. For the amide, you're just gonna get rid of the carbonyl, cleave the carbonyl off to reduce it, right? For nitrile, the nitrile carbon here is gonna be the carbon of the amine, like that, right? Where when we reduce a nitrile, it will always give us a primary amine. But when we reduce an amide, it does not have to always be a primary amine because the amide could be different. If I had a secondary amide where that nitrogen had 2 like R groups attached to it, and I reduced it, I would get a secondary amine instead, right? So depending on what your amide is, you could have a primary, secondary, or tertiary amine, right? But a nitrile will always give you a primary amine. So a concept to understand here for this derivative is that acyl halide and anhydride are the top 2 most reactive derivatives, right? They don't require acid catalyst, they don't require base catalyst, or they don't require heat to go through, right? And they can react with the weak nucleophiles, neutral nucleophiles like water, alcohol, and the weak reducing agents, weak organometallics. So sodium borohydride, the weaker reducing agent, is going to have no reaction with the weaker derivatives, right? So the weak cannot react with the weak, but the strong can react with the weak. So if we reduce the acyl chloride, we could reduce that to primary alcohol, anhydride, primary alcohol as well. Right. Now, once we move on to the other 2, these 2 reagents here create aldehydes. They form aldehydes. Dibol will only react with 3 of these derivatives. Dibol will only react with ester, amide, and nitrile. Only these 3. Always amide and nitrile into the aldehyde. Right? No reaction for the other derivatives. When you see this bulky reducing agent, that's also going to create an aldehyde. But the derivatives that it's going to react with are the most reactive derivatives, the acyl halide and anhydride. And then no reaction for the other ones. Like that. Okay. Any questions on this reduction table or the derivatives? Yeah, so that's going to be like some other thing. Like you would expect Dibol to react with all of these because it can react with the weakest, least reactive derivatives, but it doesn't react with the most reactive derivatives. And it has to do something with its structure and how it reacts with these chemical like functional groups. I'm not like too sure why it only reacts with those three and it doesn't react with the other three. It's not as intuitive as like the strong reducing agent reacting with all of it, the weak reducing agent only reacting with the strong ones. Like this one makes sense, right? Like the bulky ones, it's a very bulky, weak reducing agent, so it can only react with the most reactive derivatives, no reaction for the weak reducing agents. But diol is the weird one, where I would like always keep diol in mind, where it only reacts with the bottom three, the least reactive derivatives, right? So whenever you see diol, always think of three functional groups: esters, amides, and nitriles. When you have any of these three reacting with diol, you always get an aldehyde. Right? I'm not sure why it doesn't react with the other ones. Right. And you don't have to worry about the mechanism of this as well. So just know that when you see diol, the weird one, it could only react with these three to form the aldehyde.
Brian, don't you think it's weird Dibel wasn't in our practice problems at all?
Oh, it wasn't in the practice sums at all?
I don't think so.
Oh shoot. Did he teach it? I'm not sure. Did he did? Oh, okay. So if it's not in the practice problems, did Farahat create those practice problems himself, or did he pull them off of the textbook?
He takes some off the textbook and some of them I think he makes himself, but a lot of them are really similar to the textbook.
Yeah.
The textbook only uses a little bit of diol. They don't use diol that much.
Uh-huh. The achieve homework had some diol questions in there, right? The achieve homework?
It had like diol PCC,
Diol PCC. Oh,
Jones,
okay.
and everything, a lot of stuff.
I see. Yeah, I would still know it just in case. Yeah, even though it didn't show up, I would still know what diol does. Yeah. Okay. Now let's go over the other chart, the organometallics with carboxylic acid derivatives. Organometallics react with carboxylic acid derivatives. Okay, I'm gonna copy and paste this. Oh, I just remembered he did teach another reducing agent, but I haven't seen him like I haven't seen this in the practice problem yet, which is BH3. And BH3 is a chemo selective reducing agent for carboxylic acid. Right. So let's say you have this structure right here, and you want to reduce it into this structure right here. We see that we only reduced the carboxylic acid into the primary alcohol, right? But if we tried doing LiAlH4, lithium aluminum hydride, that's going to reduce both the ester and carboxylic acid down into the primary alcohol. But we don't want that. We want to maintain that ester. So if you try something weaker like sodium borohydride would not react with any of them, right? Because these are the less reactive derivatives, and sodium borohydride will have no reaction with these two. So if you only want to go for the carboxylic acid, then you just use BH3, right? But I haven't seen a practice problem on that yet, and this is like a farahat thing. Like I've never seen this until farahat's class. Have you guys seen this again besides lecture, like in practice, like in Achieve or like some other practice problem? I think Maria Jones, she her worksheet had this reagent practice down. He pointed it out in lecture. Let's see. Okay, so just in case it shows up. Yeah.
Sorry, isn't there other reducing agents that he used? I remember he said there's like a metal reduction. If you have a benzene, like a nitrobenzene, could you use like
Oh,
iron or SnCl2?
yeah. If you have nitrobenzene, you could reduce this into aniline, NH2, with 3 reducing agents. You could either use H2PD or iron HCl or zinc, mercury, HCl, clementine reduction. Right. So this is 118B, from 118B, reducing an EWG into an EDG, meta director into an orthopara director, using one of these 3 reducing agents. But this is good for the chapter 21 chapter, because this is how we could prepare amines. Right. In the product here, we created an amine, and then with this amine, we could do the reactions that we learned. Reductive amination with another carbonyl, manic reaction, Hoffman elimination, yeah, the chapter 21 reactions. Right. Yeah. So let's say we have these derivatives again, and there's 2 organometallics. There's a strong type and a weak type. Right. Can you guys tell me which one you guys think is strong, which one you guys think is weak?
Would Grignard be strong and then weak would be, was it called Gillard's?
Yeah, Gilman or organocuprate.
Gilman.
Strong would be Grignard or MGBR or organolithium or Li. The weak one is going to be organocuprate or Gilman reagent. R2 CuLi, Uli. Second step, acid workup. So the weird thing about the organometallic is that it's going to attack 2 times. Right? When we have an acyl chloride, it's going to add the new R group, the R prime group, 2 times, which is why we see the R prime group like 2 times there. And the reason why is because I'm going to show you an example problem. If we have this acyl chloride right here, and we react it with this Grignard reagent, acid workup, this is the star or nucleophile, this is the dot, star attack the dot, pop the double bond onto the oxygen, get this tetrahedral intermediate, connect the star and dot. Once we have this tetrahedral intermediate right here, you always have to stop and ask yourself if you can kick out a leaving group. Right? If you can kick out a leaving group, then that's what you want to do. You want to reform the carbonyl and kick out that leaving group. And let's say you can't kick out a leaving group. Let's say there were no good leaving groups there, right? Like let's say this was a hydrogen or another R group. Then the next step is to bring in the acid and do acid workup to make this into an alcohol. So you do not want to make an alcohol at this point right here, right? You don't want to protonate it because we have a good leaving group present, which allows this oxygen to reform the carbonyl, kick out the good leaving group, and get this carbonyl back, right? But we still have the new R group there, which is the first R group. But we did form another electrophile here, which another Grignard reagent is going to come in and attack. Pop the double bond onto the oxygen, give us this tetrahedral intermediate here. Right? And now we stop at the tetrahedral intermediate and ask ourselves, can we kick out a good leaving group? In this case, no, we can't, right? Because all of these are R groups, which are terrible leaving groups. Like R and H's are the worst leaving groups, right? They do not want to leave at all. So then we bring in the acid workup step to neutralize the O- into the alcohol. Right. final answer, which is why we see the new R group attached 2 times. Like that. Right. So that's the reason why we add the R group 2 times for these derivatives. Same for the anhydride. And for the carboxylic acid right here, like keep this in mind, this is a tricky one. We have a very acidic hydrogen present, and organometallics are strong bases and strong nucleophiles. But they're gonna act as a base first before a nucleophile, because acid-base reactions are one of the fastest reactions in OChem, right? So what's gonna happen is that we're going to have a deprotonation step, acid-base reaction. We're going to deprotonate the carboxylic acid into the carboxylate. And then because of the acid workup step, we're just going to go back into the carboxylic acid, right? But if they do not have that acid workup step there, and they just have the Grignard reagent, you would stop here as the answer, the carboxylate.
So
Right.
would you say no reaction for that?
You can say no reaction, or you can draw out the carboxylic acid again. This was actually like a problem for Helix's exam, because some people put no reaction, some people put this carboxylate, some people put the carboxylic acid, and then he accepted all of those answers, right? Because it was confusing. People were requesting too many regrades for this problem. For farahat, I would, if you see like just a Grignard reagent with no acid workup, I would put this as the answer. And if you do see acid workup, I would still put the carboxylic acid as the answer. Like I wouldn't put no reaction, because technically an acid-base reaction did happen. We deprotonated the carboxylic acid, and then we just reprotonated the carboxylate into the carboxylic acid again, right? But I can see why some people would put no reaction, because like we didn't change anything from the overall reaction, right? But I would put this as the answer if there's acid workup. Now, when we get to ester, we go back to adding the R prime group 2 times. Don't worry about amide organometallics. This is for like Chem 131A or Chem 231A or B, not for 118. Right. Now for nitrile, whenever you react a nitrile with a Grignard reagent, organometallic, you're always going to get a ketone. Right. Where the carbonyl of the ketone is the carbon of the nitrile, and we only add the R group once, the new R group once of the Grignard reagent. Right. So for example, if I have something like this, I see that I have a nitrile in the reactant, a Grignard reagent on the reagent side. So I know that I'm going to have a ketone. So to predict the product quickly, my nitrile carbon is the carbonyl of the ketone, right? So if I do that, that's that nitrile carbon right there. The other R group, the new R group, is going to be the R group of the Grignard reagent, which is that right there, right? The original Grignard reagent is from the original nitrile, like that, right? And just because I showed you guys it in this order, don't get tripped up when you guys see a Grignard reagent on the reactant sides and the nitrile on the reagent side, right? He could flip-flop like these, but they mean the same thing, right? Nitrile plus Grignard reagent, ketone, right? With acid workup, right? And then the nitrile and Grignard reagent could be the reactant or reagent. They just go together to make this product here.
Brian, I have a quick question.
Yeah.
Sometimes I saw the Grignard reagent being worked up by water instead of acid. Do you know when it would work with water and when we should use acid?
Yeah. Water and acid So water is going to be mostly used with organolithiums, or actually no, water is going to be used mostly with amines when you work with amides and amines, right? Because if I have this amide right here and I try to reduce it with lithium aluminum hydride, and the acid that I used to do acid workup is H3O plus, I would reduce the amine down to this form. But because we are in acidic conditions, there's a chance of over protonating the amine to the ammonium ion right there, right? But to prevent that over protonation, we could use water instead, which is a weaker acid that would not over protonate the amine and give us our neutral amine right there. Something like this, doing a Grignard reagent, getting to the ketone, you could use either acid or water. It doesn't matter.
Okay, great, thank you.
Yeah. It's probably best to go with the acid though, because wait, this one for right here, you need acid for sure for Grignard reagent, right? Because use water for this one. You can't just use water. You need H2O plus and water together, because the intermediate for this is going to form an imine intermediate, and then you're going to hydrolyze this imine from monocyne B to a carbonyl. Like, you're gonna convert this whole imine right here, the carbon double bond nitrogen, into this carbonyl by using acid and water. And the carbonyl oxygen of the water, which I'm gonna box in red, is that box oxygen of the water right there. Right. But some professors, they are gonna assume water is there by just putting H3O plus. Like, because if you use H3O plus, it will get deprotonated to water, which you could use to do the attack, and then the whole peptide thing or proton transfer thing, deprotonate the group that you want to keep, protonate the group that you want to kick out. Step. Right. Yeah, this is only for nitriles. Like, nitriles with organometallics would only create ketones, right? Everything else would create an alcohol, and we add the new R group 2 times, right? Except carboxylic acid. In carboxylic acid, we do an acid-base reaction, right? Now, once we move to the weak organometallic, it cannot react with the weak derivative. So no reaction, no reaction, no reaction. It can only react with the strong. And even if it does react with the strong, it only adds once. It stops once. It stops at the ketone. So you could also create a ketone from an acyl chloride or acyl anhydride by using organocuprate, right? So this could be in synthesis, where if you have a ketone coming from one of these crazy 2 derivatives, like the most reactive derivatives, then you know your reagent is going to have some kind of organocuprate to it, right? When you see ketone being formed from acyl chloride or anhydride. But if you see a ketone being formed from a nitrile instead, you cannot use organocuprate. You can't use the weak one. You have to use the strong one, either Grignard reagent or organolithium reagent. Right? But here's like the table summarizing everything for organometallic. There is another chart, but that chart is a little bit messier. I think I need like a way bigger page or like a way bigger whiteboard, and that's the chart of interconverting between derivatives like carboxylic acid, anhydride, acyl chloride, ester, amide, nitrile, like how to go in between those two, and the other oddball reactions, HBZ, and Huffman rearrangement reaction. But it goes crazy. Like, I tried doing it on the iPad, notably here before. Like, there's so many arrows, like that goes everywhere for that chart. But these two are like the tables that are organized and neat that you guys could review here. But you guys are familiar with those reactions though, right? Like Fischer esterification, trans esterification. Like are you like you guys are familiar with converting between those derivatives? Okay, that's good. That's good. Yeah. You guys want to end off with synthesis problem? Okay, let's do two. Let's do two synthesis problems here. Okay, let's try this one. And the other one is going to be okay. Let's try these two synthesis problems here. Does anyone want to try the first one? Or can I hear what someone tried? Like going backwards or forwards? I don't know if there could be different routes, but let's see what you guys got for these so far.
So I'm still kind of like piecing it in my head right now.
Oh yeah, yeah.
What I would say first for the first one was to add acid. And so you'd make that carboxylic acid at the top there, and then
Mhm,
add PBr3, which will simultaneously make a Br at the bottom side, but will also make an acyl bromide at the top. And
mhm,
then once you have the acyl bromide, we need to add the isopropyl there. So
mhm.
I'm thinking about just adding the organocuprate or the lithium cuprate with isopropyl. Um, but then for the bottom, I'd have to add magnesium to extend the carbon chain, right? And then make that into a carboxylic acid. I don't know, I might be wrong on that part.
Mm, right. PBr3 would convert that into a bromine, and then you do magnesium, and then you do oh right. So when you do magnesium right here, this would create a Grignard reagent, which there is an electrophilic thing in the way, so it's gonna do an intramolecular reaction before attacking a carbon dioxide, right?
All right. Yes.
So yeah, I just realized that I made a typo here. That should be a primary alcohol right here. Oops. Right. So so instead of doing a Grignard reagent, how can we convert this primary alcohol into this carboxylic acid here?
Chromic acid.
Yeah, Jones reagent. Okay. Now once we have this carboxylic acid, what reaction do you know that adds a bromine alpha to it?
Easy.
Yep, HBZ reaction. HBZ. Right. So this is one way that would work, but let me just make sure and write everything out and piece it together. Let's see here. That's good. That's good. Nice. Nice.
But could you also use Br2 with trace palladium? Is that the same thing as HVZ?
PBr3 trace. I think it was like water or something. NaOH water. I forgot the other one. PBr3 trace.
I think it was Br2 trace. I
Oh
might be.
yeah, PBr3 trace or BR2 trace. You can
Oh,
see as either way. Um, there was another reagent, another thing, right?
is that the same as HVZ there?
Yeah, that's the same as
Oh,
HVZ. These reagents are the same as HVZ, the Helmholtz-Zielinski. PBr3 trace or BR2 trace.
gotcha.
First step is that, second step is water for HVZ. Helmholtz-Zielinski. Right. Okay. So hydrolysis with acid, water, and heat. Carboxylic acid, OH. Full PBr3 to get the acyl bromide, or you could use SlCO2 to get the acyl chloride, the most reactive derivative. But that would also react with the alcohol here. So I just realized that this route would not work because the PBr3 or the SlCO2 would also convert the alcohol um into the halogen, bromine or chlorine. Right. So, and that would mess everything up because we need Jones to make this into a carboxylic acid. And if we do have chlorine or bromine attached to it, and we try to do the magnesium carbon dioxide thing, the magnesium is going to do an intramolecular reaction with the carbonyl, right? To prevent the alcohol from being converted into a bromine and chlorine, you would have to use a protecting group and deprotecting group, like protect the alcohol and deprotect it, but that's going to be like too many steps. So let me show you what I had in mind, and let's see if it works, because like there might be some problems here as well. But but yeah, that's okay. Let's see. Um, so I saw a ketone here, and then I saw a nitrile. What reagent do you guys did we just go over that can create a ketone from a nitrile using? Yeah, there is a problem here. Okay, so this is a terrible problem. This is a terrible synthesis problem. Yeah, because what I originally thought was to do a Grignard reagent, right? Like organolithium, doing this MgBr, first step, second step, H3O plus, to get straight to the ketone, like this, right? Where the ketone carbon is the nitrile carbon. But the Grignard reagent here is a strong base, strong nucleophile, right? But it's going to act as a base first before nucleophile. So this is actually going to deprotonate the alcohol first to get the deprotonate alcohol and not react with the nitrile, right? So this synthesis problem is no good right now. Okay, let's get rid of this. SlCO2 not work either. Yeah, so SlCO2 would not work as well because it would also convert the alcohol into a halogen. SlCO2 would convert the alcohol into chlorine. Yeah, right. If I were to use a protecting group and try to make this work, it's gonna be pretty long, but this is what I would do. Right, before doing the PBr3 or SlCO2, I would protect the alcohol by doing acid-base reaction, H2SO4, just those reagents, and creating the ether. Right, the acid would make this into a carbocation. The alcohol would attack the carbocation and create this ether. Okay. Now this is unreactive. Then we could use PBr3 or SlCO2 to create the acyl halide. And that would not react with the ether, right? That protects the alcohol. Now, once we have that, we could do the organocuprate or Gilman reagent that Peter said earlier with copper lithium. And second step, acid workup to get the ketone. The ether is still there. It did not react. And then from this point right here, we're going to deprotect the ether, the alcohol, by doing acid and water. Right, H3O plus water, which is going to convert that ether back into the alcohol. And then from this alcohol, we do drones to convert that alcohol into the carboxylic acid. And then from the carboxylic acid, we do HVZ, Helvor-Zielinski, with first step PBr3 trace or Br2 trace. And then second step, water. So if I were to name these, hydrolysis of nitrile first, protect alcohol, protecting group, protect the alcohol from the PBr3, like acyl halide formation, or SlCO2. Gilman reagent to convert the acyl halide into the ketone, the weak organometallic reagent. Deprotect alcohol. Jones, and then HVZ. Okay. Yeah. Let's see. Okay. Let's try this one. What would you guys try for this one here? How did we get this new R group? From this acyl halide. Right. Don't think about the alcohol. Like imagine Like how can we get a new R group to this acyl halide and the carbonyl could still be there, let's say. Right. Let's say the carbonyl is there and the R group is there. What reagent can we use to create this ketone from an acyl halide? Yep, CuLi, Gilman reagent. Where the new R group is going to be to CuLi. Second step, H3O plus to get that ketone. And then what can we do to convert this ketone into the alcohol? (118A). Are we oxidizing, reducing, acid base, nucleophile, electrophile?
Can you use lithium aluminum hydride?
Yep. You could either use lithium aluminum hydride or sodium borohydride for this. Sodium borohydride is also a strong enough reducing agent to reduce ketone. Now we see that we have a secondary amine here, and we made a more substituted amine here. This is a chapter 21 reaction. What reaction do you guys know that will make the amine more substituted? What method? What strategy do you guys know of? What reaction? It might help if we find out what's the similarity between the reactant and product. In the reactant, our amine was this portion, which is this portion right here of the product. Right, so the new portion is this one right here, and if I make a split right there, where could this have come from? This new substituent on the amine. What reaction did we do? Hoffman rearrangement. So Hoffman rearrangement is going to react a primary amide with Br2 base in water and get rid of one carbon and make the primary amine. Right, so Hoffman rearrangement is having a primary amide reacting with Br2 base water and getting the primary amine, where we get rid of that carbonyl carbon. In this case right here, we don't have a primary amide, and we don't have a primary amine in the product. Right, if we want to make another amine where that other amine is more substituted, we want to do reductive amination. Right, where this is going to be our amine right here, and our carbonyl is going to be whatever I put in blue right there. That's the carbonyl in acidic conditions, and NaBH3CN. And that's going to substitute this whole carbonyl with the amine minus one hydrogen. And let me put one equivalent of this, because if there's excess, then that could also react with the alcohol. Right, but then there's a competition between nucleophiles here. Amine is a stronger nucleophile because it's less electronegative than alcohol. Right, but this last reaction here is reductive amination because we have an amine reacting with the carbonyl to create a more substituted right here. We're substituting this carbonyl with the amine minus one hydrogen like that. So this was a little bit tricky because you're used to seeing reductive amination the other way around. You're used to seeing reductive amination with the carbonyl as the reactant side and the amine in the reagent. Right, so this flipped it around. Gilman reagent, reduction, and then reductive emulation. Like one equivalent to just react with the stronger nucleophile amine, not the alcohol. Okay. Any questions on the synthesis round? Okay. Are you guys going to what time do you guys plan on sleeping? Your exam is in like 9 hours. 7:30 a.m. First thing in the morning. Are you guys gonna study more or you're cooked? Have you guys let's see. Yeah, I recommend like doing all the farahat practice problems he posted on his canvas. Sleep now, wake up at 4. Shoot. Yeah. Wake up at 4, study a bit, cram, and then take the oh yeah, I forgot this is the midterm, not the final. Take the midterm, take the midterm.
Brian, this feels like a final.
I know it feels like a final. I thought it was a final, but then I just realized it's just the first midterm. Oh,
I'm
shoot.
hoping that the final, I haven't looked, but I'm hoping it's not 7:30 a.m. That would be real nice.
Yeah, I know. You guys need to sleep, like, and then have some time to study in the morning before the exam too. But yeah,
So much.
uh-huh.
Thank you so much. I really appreciate the help.
Yeah, no problem, guys. Good luck tomorrow. Trust yourself. Do all the problems that you guys know how to do first. If you look at the problem and you're like, this, like you don't know what's going on and you need some more time to think about it, skip it. Do all the ones that you can do really fast, and then go back to the ones that that will take more time. Just to make sure you have like more time to finish the exam. You know. Yeah. Good night,
Thank
guys. Good night. No problem.
Thank you so
Bye.
much.
No problem. Hello, hello.